I want to take a moment to highlight our solutions portfolio at Hawkridge Systems. I'm Tim Milo. I cover the Simulation Suite sales, which is this piece of the design product portfolio over on the right. But I really wanted to make sure that we highlighted that we have a full design to manufacturer portfolio. Many of you are probably familiar with us through our SolidWorks CAD offerings and the other products through the SolidWorks brand. In the Simulia lineup, today we're really going to zoom in on Simulia CST for connected device applications and kind of touch lightly on what's possible with some of the other Simulia offerings, but really just wanted to take this opportunity to let you know that we have kind of high-end offerings across CAD, data management, simulation, and manufacturing, whether it's the CATIA CAD offering Innovia for data management or Simulia Abacus, CST, and XFlow on the analysis side. So with that out of the way, and I'll get to the introductions of my Dassault counterparts. Today we have Mathilde Iman here to present for the kind of the backdrop of why we're putting this offering forward. She's a solutions manager from Dassault's high-tech industry team. So she's going to go into the industry background and challenges. Derek Nunes is a CST sales consultant from the Simulia brand, and he's going to give you a deep dive into the electromagnetic solution offerings. And then last, Mahesh Tarag is a director of simulation initiatives for Dassault Systems, and he's going to cover the balance of the solution, including some of the complementary products from the Simulia brand. So with that, I'll hand it over to Mathilde.
Thank you, Tim, for the introduction, and hello everyone. Thank you for joining. So as said, I'll start first by giving you the overall context of this webinar. So what is the high-tech industry, its business drivers, its simulation challenges, and how can we help high-tech companies actually answer those challenges? So I guess we're all pretty familiar with the high-tech industry, as we all carry around many connected devices. But it's not only about those connected objects. High-tech companies are also engineering many components and subsystems. And what they all have in common is that they face a huge pressure to innovate. The high-tech market is indeed a highly volatile market. The consumer's expectations are evolving very rapidly. They're always looking for new features and form factors. And poor product experience, or even worse, an early product failure can have catastrophic outcomes on the company's revenue and reputation, because high-tech consumers can very easily turn to competition. Moreover, to answer the market thirst for innovation, OEMs have to engineer more and more complex products with an ever-increasing component density and ever thinner and lighter designs. The foldable phone you can see here is a good example, because imagine how complex it is to have the electronics going through the flexible part and also to engineer a phone robust enough to resist 100,000 volts. Finally, the high-tech industry is characterized by a short design cycle if we compare to automotive and aerospace industries, because companies have many product lines and they usually launch one new product every year. So they face a huge pressure to be first on the market and to accelerate the development of their product. So what could actually help high-tech manufacturers face those challenges? Well, one element is simulation. Simulation is key to avoid time-consuming and costly physical prototypes and also to ensure product reliability. But simulation also comes with its own challenges, because simulation engineers that want to verify the product reliability very early in the design cycle have to perform a lot of simulation. As I said previously, companies have many product lines, but also many product variants, and in some cases engineer their own components. So I let you imagine the number of simulations they need to perform to verify all those systems, subsystems in all different domains, like electromagnetic, thermal, fluidics, and so on. Products are also defined by an important number of consumer and regulatory requirements, and some performance indicators can actually affect one another. For instance, we all want highly connected objects with Wi-Fi, Bluetooth, 4G, and soon 5G. But at the same time, we don't want radiation absorbed by the human body increasing or interferences appearing. So how can simulation ensure we find the best trade-off and at the same time that we verify all those requirements? Finally, discipline experts often work in a disconnected manner with heterogeneous landscape of tools, methodology, data formats. So this lack of continuity can actually result in the loss of data, but most of all in the loss of time. How can simulation ensure this continuous and rapid validation? Well, the answer is the Simulia portfolio from Dassault Systèmes can help those high-tech companies face the simulation challenges we just saw previously. It not only integrates Multiscale's Multiphysics technology, but also a unique environment to connect all the simulation stakeholders and all the simulation data in one single place. So this will hugely improve the productivity. So all those simulation technologies are either available on the 3D Experience platform or using our standalone tools connected to the 3D Experience platform. With this broad Simulia portfolio, we have defined the highly virtual prototyping solution that is the end-to-end simulation solution for high-tech companies. It goes all the way from planning the validation strategy to executing the different simulations. So electromagnetic simulation, structural and thermal simulation, all the way to assembling those different physics simulation in reusable processes to explore the whole design space and find the best trade-off. So now I will let my colleague continue and give you an overview of the electromagnetic capabilities we have here in this solution.
Thank you very much, Mathilde, for setting the stage. Just very quickly, as Tim mentioned in the beginning, my name's Derek Nunes, and I work at Dassault Systems. And what I'm going to go through in my portion is kind of the electromagnetic simulation deep dive, as well as explaining the underlying technology there. So, next slide. There we go. Okay, so the first thing that I would like us to think about when it comes to simulation is reducing risk by understanding problems before you actually start to build. That is one of the primary things that we use simulation for, and a fantastic example of this for electronics is thermal problems. I'm sure we've all heard of things in the news where things could be sparking or smoking because of short circuits or spark gaps, whatever that may be. You're sending too much electrical energy somewhere and it can't handle it, lights on fire. Nobody wants that. That is not good publicity. Not all good publicity is good publicity. So having a deep understanding before you actually build something is huge. So in light of that, having this understanding before you build something allows you to reduce the amount of physical tests. Now, physical tests are costly. They are time consuming, and it's really kind of the older way to do workflows where you're just kind of brute forcing it with physical designs. Having some simulation at the earliest possible stage increases the speed of your designs. The go-to market is much faster, the quality, and maybe most importantly is reduces costs, because every company and every person, of course, is very concerned with that. So going to the third one, improving product quality. The way I like to think about this is kind of the build, test, tweak workflow, where engineers have done that historically. You build it, test it, okay, that didn't work like that, so we need to go back and change it. What simulation allows you to do is to understand, again, going back, understand things so early on that you can get more creative. Now, high tech is all about being cutting edge. You know, what's the newest, what's the greatest, what's the most creative, you know, that is where we really can help out as far as kind of improving product quality is concerned, let alone validating it before you build it. And a really interesting one as well is regulatory compliance. Mathilde touched on it very briefly, but that's really specifically looking for what's called EMI, electromagnetic interference, which is if you're too susceptible to outside radiation, you know, you're the victim, so to speak, or are you the one, the villain, who is radiating too much? So that is not going to allow you to go to market because of strict FCC standards. It's not just a slow go to market. If you can't figure out why, then you won't go at all. So, okay. Now, just to set the scope a little bit, we're going to talk about sensors, antennas, and we're also going to talk about electronics design analysis specifically. I didn't want to limit the scope too much here. So there's a lot more our technology can cover, whether it's GPS, RF connectors, radar, cables, very important. Obviously circuit boards, antennas, but a really good example of how simulation helps with this is an example called SAR, specific absorption rate. If you see that image on the bottom in the middle, that shows a Dassault Systems human bio model to be used for understanding the electromagnetic effects on the human body. Now, you can't even physically test that because we don't want to fry anyone's brains, right? We don't want to hurt anybody. So having this realistic and accurate simulation done beforehand is truly critical. There are some spaces where you can't even do the physical testing. So perfect. All right, moving on to the next slide. I want to bring the audience in a little bit on the ground floor with us here and provide you with a peek under the hood of the technology driving this workflow. Now, I worked at a company called CST for 4 years before Dassault Systems acquired it, which sold full 3D EM simulation software that can cover really anything you can think of at the highest possible level of fidelity, accuracy, and efficiency. So I wanted to give you sort of a peek under the hood of, because it was still relatively recent for Dassault, what's driving this entire workflow, the Rolls-Royce engine, so to speak. So the reason CST is so good is because it has something called complete technology, which really just means you have the right tool for the job. Really quick example, if you're building a highly resonant, narrow band, electrically small antenna, you're going to want to use a frequency domain solver. You want to use that numerical method. If it's broadband, electrically large, you're going to want to use our time domain method. Now, not many tools have, let alone either of those two, or the other 15 that we offer in the base package within CST. So having every single tool for the job allows you to use less hardware, simulate faster, less expensively, but even more, you never need to worry about what the problem is. It covers everything from statics to gigahertz, terahertz, even into the optical frequency. And the analogy I like to use is we all know the brute method approach with simulation. You can pound in a nail if it's sticking out of a piece of wood with the butt end of a screwdriver, but you would much rather use a hammer. You want the right tool for the job. So moving on. A quick just backdrop of something we all know, which is that the world is becoming more electrified by the day. I wanted to break it down to 2-3 things I saw as maybe the most important now and in the future, which is variability in product complexity, because we want more electronics. We want it to be able to do more things in a smaller space. That is a highly dense set of electronics, which when you put something that close together, it's going to have its own unique challenges. So that's something new to the world that we need to think about in a different light. The next thing is the Internet of Things. I'm sure many of us have heard of that, IoT. The Internet of Things just means antennas on things. Antennas are the mouthpieces and the ears of electronics. That's how things talk to each other and how they listen. It's truly as simple as that. And as we all know, everything's connected now. So that means there's tons of antennas on varying varying range of products, more and more every day. And the next one is autonomous and smart devices. So the example I want to use here is if it's a self-driving vehicle, maybe it's using a GPS antenna to know where it's going down the road. But what if a car all of a sudden pulls out in front of it? The GPS isn't going to detect that. You need a sensor. Sensors detect the physical stimulus of the world, whether it's weight or distance, whatever that may be. Now, all these things need to work in conjunction together, which again offers some unique challenges, and is something we need to really think about early on. So moving on, this is a great example for sensors. It's something we can, again, I'll relate to. This is a touch screen. It's using capacitance on a cell phone to measure with sensors a physical stimulus, which in this case, instead of the truck pulling out, right, it's a finger. It's saying the finger went down, it's on the screen, so it's scrolling, or it clicked that like button on social media. Whatever it is, that's all sensors. And we use it every day, maybe without even thinking about it. So moving on to antennas here. The way I like to think about antennas is it's not just how it works in a vacuum. If you're putting it in an anechoic chamber, is it going to function to measure the gain, the impedance, the near fields, the far fields, all things we can do extremely well. It's what if it comes down from corporate, you need to move that antenna down an inch. How is it going to affect it when you place it somewhere different? And how is the installed performance going to be affected? The technology we have, I cannot say this enough, is as good as it gets for antennas. So if you're doing antenna design, you're in the right place if you're looking at CST or Dassault's EMAG technology. And as far as electronics design analysis, this is a good slide that shows the whole workflow really. That's when you look at a whole bunch of different factors for electronics, starting off with the 2D circuit schematic simulation, to importing your 3D PCB board, to doing some quick design rule checking, like, oh, traces are too close together. We know there's going to be crosstalk, to the integrity of the signals, the losses to see if it's working efficiently, to the power delivery network. Is it providing enough power? Is it providing too much power? Following up nicely with the FCC thing I mentioned earlier, EMC compliance check, which I'm going to get into briefly right now. So the thing to remember with EMC is the C in EMC stands for compatible. The I in EMI stands for interference. If you're EMC compliant, that means it's good. If you're dealing with EMI, that means it's bad. So it's so critical because you can't go to market because of these FCC standards, because 50% of electronics do not pass on the first time. Now, this can be panic mode for people in some companies because electromagnetism is invisible. You might not know where the radiation's getting in or where it's leaking out. You need to visualize that somehow, otherwise you're kind of just guessing, which is not the place any company wants to be in. And a nice example, and of course it can't be launched. And a nice example of that, another thing we use every day, I've been using cell phones a lot, but it's the thing people use the most, is here. You see the FCC compliance standards, you can look it up on your phone. And even if you take the cover off the back, like you were gonna take out the battery, you see those FCC requirements there. This is critical. You need to make sure you're compliant well before you get into the late stages of building. And lastly, to wrap this entire thing up, when CST was purchased by Dassault Systems, next slide, please. When CST was purchased by Dassault Systems, the first thing they looked at was, okay, how do we make sure that CST can work well together with this new Dassault Systems portfolio? And boom, the first thing you think of there is SolidWorks. Since the acquisition was announced, they've already created a bi-directional parametric link with SolidWorks, where if you're a SolidWorks designer, it's really good at using that tool, but you can't run any EM analysis. It's going to update. If he makes changes to the CAD, it makes those same changes to the CAD and CST, and vice versa. So it's all about playing well together in this suite of tools, making workflows faster, more efficient, and more effective. So in light of that, thank you for listening, and I will pass it on to Mahesh.
Thank you, Derek. Tim, are you going to launch a poll, or will I wait for it?
Yeah, thanks. That's great information, Derek, and interesting to me to learn how much trouble people have at the first shot at EMC testing. We have a quick poll to see what people are currently doing for their EMI and EMC concerns. I'd like to hear from the audience what they're doing, whether they're testing in-house, outsourcing, or running simulations in-house or sending them out. So it looks like we have a few respondents. Looks like most people are outsourcing testing. It's pretty interesting that so far nearly the same amount of respondents are outsourcing and running this themselves. I'll give it just a few more seconds here as we get some more answers trickling in. And we're up to about half voted. So what's interesting there is 70% of our respondents are outsourcing physical testing currently. That's great. Thanks, Derek. I'll pass it over to Mahesh at this point.
Thank you, Tim. So before I get started, I would like to start by showing you guys a video of the device structural performance solution.
Consumers today are demanding products that are more reliable and long-lasting, even as functionality and performance expectations increase. Increasing product complexity amidst shortened development cycles accentuates the problem for manufacturers to come up with a device design that is reliable and can withstand everyday use and abuse. Mobile devices in particular are often accidentally dropped, which can damage the device and lead to dissatisfied customers. Such issues can spread quickly through social media and leave a lasting impact on brand reputation. In order to avoid these pitfalls and maintain consumer loyalty, manufacturers must design products that are robust and can withstand the most abusive use case scenarios. To achieve all this, Dassault Systèmes provides a comprehensive set of realistic structural simulation solutions with accurate physics to help engineers quickly evaluate the performance of a given design and choose between alternatives without the need for expensive physical prototypes. Our end-to-end digital solution lets you define different structural test scenarios such as drop, crush, bending, twisting, and vibration. These allow you to experience product performance virtually and identify and eliminate any late design issues. As a result, you can reduce field failure rate and associated warranty costs by 50% or more. Design exploration with integrated simulated data management makes it possible to study hundreds or even thousands of alternatives and narrow down the design space to a handful of top-performing options for further evaluation. Our unmatched portfolio of structural analysis solutions on the 3D Experience platform provides seamless collaboration between analysts and designers, whether they're on-premise or on the cloud, accelerating the design process from months to days. With device structural performance industry process experience, manufacturers can be confident that their products are robustly designed to meet the most demanding consumer expectations, on time and on budget.
Okay. The video you just saw shows how device structural performance enables you to significantly accelerate innovation through virtual testing and collaboration. The device structural performance solution is powered by Simulia Abacus technology, which many of you might be familiar with, which can accurately predict the behavior of complex consumer electronic devices, leading to product designs which are robust when subject to accidental misuse, as you saw in the video. In addition to predicting in-use behavior, device structural performance solution can also be used to optimize component manufacturing and product assembly. So going through some of the workflows that this solution has, the first one is by doing component manufacturability analysis, you can reduce manufacturing costs by 20% or more. By leveraging the rest of the workflows such as device strength and stiffness, water immersion, drop test, fatigue, and durability, we can significantly reduce the physical testing and then can also reduce the field failure rates and associated warranty costs by 50% or more. As a result, you can accelerate time to market from years to months. Looking a little bit deeper into the solution, as you know, the high-tech devices we have today have a wide variety of materials in a very small enclosed space. We have comprehensive technology that can enable accurate modeling of these materials, leading to accurate results. We have the capability to model different types of materials, from metals to plastics to elastomers, solder joints, adhesives, and glass. The video you see in the middle of the screen is a ball top simulation onto an LCD screen, where the simulation is actually simulating the crack initiation and propagation in the glass in the LCD screen. In addition to this, we also have something called material calibration app, which enables you to take your material test data and then convert that into simulation material properties ready to use in any of those workflows that we talked about on the previous slide. No design of a high-tech device is complete without taking into account its thermal performance. It's really critical to have an optimal thermal response for these high-tech devices, as you know. So using our device thermal performance solution, you can design thermally efficient devices and subsystems for a full range of operating conditions by exploring optimal cooling strategies with CAD embedded FEA, CAD embedded CFD. Going through the different workflows here, you can quickly improve the thermal performance of individual components during conceptual design and accurately predict the thermal response of complex PCB layouts that Derek was talking about, leveraging the full translation of ECAD to MCAD. And then you can improve the device structural performance under thermal loading by easily applying your CFD loads onto FE model. And finally, you can improve the device reliability with better than thermal design, for example, by predicting the fatigue life under thermomechanical cycles. So in essence, with this solution, you can significantly improve customer experience, meet regulations, avoid lawsuits associated with safety standards. To put it all together, imagine having a single CAD representation of the design you have available to multiple teams for rapid trade-off studies over multiple design concepts, and more importantly, multiple physics disciplines from EMAG to structures to thermal. This example basically covers a similar use case where you have a cell phone where you have an aluminum support frame that's added for structural rigidity. And then the reference model is updated in the EMAG model that the EMAG engineer is working on, where he or she finds unacceptable antenna performance resulting from the frame. Then a decision was taken to update that model, that frame, to a plastic frame, resulting in improved antenna performance. Then the model is easily taken by the structural engineer who runs the stiffness analysis and figures out that there's loss of stiffness in the fracturing of the display happens. So the solution is to thicken the display thickness, and which results in modification of the case to prevent failure. Then the same model can be easily taken by the thermal engineer to make sure that the thermal requirements are met easily. So the solution that we have, the solution that Mathilde was referring to as well, the whole multiscale multiphysics framework, basically enables you to rapidly evaluate interdisciplinary design options and reduce the time taken from months to days. So in summary, I'd like to summarize what we've discussed so far. As Derek was talking about early on, we have the CST Studio Suite as a one-stop comprehensive technology to address all your electromagnetic needs, and how it helps to avoid late-stage design failures and reduce risk, and more importantly, achieve the regulatory compliance that is needed to put these high-tech devices on the market. And then we talked about how leveraging the device structural and thermal performance powered by Abacus solver and our CFD solvers you can make early and collaborative design decisions that basically help you achieve the product performance that you're looking for. And we also discussed about accurate material models that deliver accurate results for these devices. And then finally, whether you're using a 3D experience platform or you're using some of the tools so that we have the traditional tools that Dassault has, we have full interoperability with SolidWorks, where you can leverage a single CAD representation in the software you love in SolidWorks, and then share that with across multiple design teams, as well as multiple simulation teams dispersed geographically over the world, in the world. Derek also highlighted the bidirectional parametric interface that we have between CST and SolidWorks. And also, as you saw from the video, our solutions help you manage the simulation data and the processes resulting from those hundreds and thousands of design iterations you can seamlessly do as you optimize your products for robust performance. That's all we have, and thank you for your time, and we will be glad to do any deep dive on any of these topics as a follow-up. Over to you, Tim.
Yeah, thanks. Thank you, Matilde, Derek, and Mahesh for presenting some great information about the challenges in connected to device design, as well as some great solutions available from Dassault. I want to take a moment to highlight our contact information for Hawk Ridge Systems. For additional information about any of the areas that we covered today, please feel free to reach out to your account representative, and we'll arrange a consultation with a product expert and kind of take a deeper dive into your questions. And also in the following, we're going to take a few moments for Q&A. One more thing I'd like to highlight is we'll send out a copy of the webinar and a link to the webinar, and we have all of our Hawk Ridge content available on our YouTube channel as well. Last, your Hawk Ridge technical support contacts are here at the bottom left of the screen. Just visit hawksupport.com. And so now we'll open it up for questions. So we'll take a few minutes to kind of watch for questions to come in and field anything that we can. There's a couple that had come in through the course of the webinar. So I think this first one I'll probably field over to Derek. Do you have a solution in CST for electric motors?
The quick answer to that is yes, we do. We have multiple solutions for magnetics and low frequency. That kind of touches upon the complete technology aspect. So the short of that is yes, absolutely.
Okay. And then another question that we had was, do you have piezoelectric simulation in CST, and what about drop tests? I'll also pass that one over to Derek.
Yes, we do. But as far as like physical drop tests, I think that would be more of an abacus application. We have some thermal and structural. Like if you're running a certain amount of current through a small piece of metal, how hot is it going to get? How is it going to deform? So absolutely. But I would say for anything like a drop test specifically, you would want a solution like abacus to do that. We're very much the EMAG focus there.
To add to that, Derek, yeah, the piezoelectric material, you can actually, if you're using in the device, you can using the device structural performance, you can do drop test and model the material as well accurately, the piezoelectric material.
All right, we have a question about compatibility with other EMAG solutions. The question from Bob is, can I bring in my existing ANSYS HFSS files over to solve in CST?
I'll take that one. 100% you can do that. Any files you're looking to bring in, you're not going to find any restrictions. It's very open. So there should be no problems you encounter whatsoever for bringing in any sort of CAD.
All right, and looks like we've run through our questions there. Thank you all so much for attending and for the great presentation.